Okay, let's jump right into this explainer. Imagine you're a network engineer and you've been handed the ultimate high-stakes puzzle, keeping a mobile connection alive. We all just kind of assume our phones will always work, right? But behind the scenes, there's this incredibly complex ballet of protocols keeping everything glued together. Today, we're popping open the engineer's toolkit to see exactly how GSM network protocols pull off this seemingly impossible feat.
Seriously, think about the physics of it for a second. How does a phone moving at highway speeds never drop a call? As an engineer, you're constantly fighting signal interference, terrible battery life on the user's device, and rapid movement across entirely different network zones. And yet the user? They expect absolute perfection. Crystal clear voice, zero data hiccups. To actually deliver that, we have to rely on a very strict, robust set of radio resource procedures.
So here is the agenda for our toolkit today. 1. Mastering power control logic. 2. Handover decision logic. 3. Complex handover scenarios. 4. Optimizing channel capacity. 5. Mobility and location updates. And 6. Key performance indicators.
Section 1. Mastering power control logic. Mastering the basics.
Your absolute first line of defense to stabilize any connection is power control. But to make those split-second decisions, you need constant intelligence. So every 480 milliseconds, data gets fired off to the base station controller, which is basically the network's local brain. On the downlink, the mobile station measures signal strength, quality, and neighboring towers. On the uplink, the tower measures incoming strength, quality, and distance. That distance measurement, it uses timing advance metrics, and it is absolutely crucial. If the network doesn't perfectly sync your phone's transmission timing based on how far away it is, packets crash into each other. That literally cripples your network throughput and makes handovers fail instantly. This rapid 480 millisecond feedback loop is what makes real-time adaptation possible.
Now, you really have to distinguish between raw power, which we measure in decibel milliwatts, or dBm, and the actual clarity of the data, which is tracked by the bit error rate, or BER. You can have massive signal strength, like full bars on your screen, but if there's heavy interference, your bit error rate shoots up and the call sounds like total garbage. Balancing a strong signal against a low BER is the ultimate deciding factor in whether a call lives, dies, or gets handed over to another tower.
To manage this, engineers set strict upper and lower thresholds for both device power and tower signal strength. As distance increases and the signal drops toward that lower threshold, the network issues a command to increase power and the phone steps up its transmission. But if the phone gets too close to the tower and hits the upper threshold, the power gets stepped right back down. This dynamic power adaptation is a total game changer. It saves the phone's battery, and it drastically improves the overall carrier-to-interference ratio across the entire network by stopping devices from screaming louder than they actually need to.
Section 2. Handover decision logic. When power control fails.
So, what happens when tweaking the power just isn't cutting it anymore? Well, a handover, which is automatically switching a call to a new traffic channel during speech, is strictly your backup plan. It eats up massive network processing resources. So the logic goes exactly like this. Step 1. Attempt power control to stabilize the link. Step 2. Evaluate if that power control is actually helping. Step 3. If the power is maxed out and doing absolutely nothing, only then does the network automatically switch the call to a new traffic channel. It's an amazing feature, but we really only use it when our primary defense completely falls apart.
Section 3. Complex handover scenarios. Moving across zones.
Handovers aren't always a simple jump from Tower A to Tower B. Sometimes you'll trigger an intra-cell handover, which changes the carrier frequency within the exact same cell. Now, why force a channel change if the phone isn't even moving? You do this primarily to reduce code channel interference or to run routine maintenance on that specific piece of network hardware. It's a proactive little trick to keep quality high without the user ever having a clue.
But then we have the complex reality of actual mobility. A stationary phone just attaches to a single mobile switching center and visitor location register. Simple, right? But as a user moves from, say, cell 1 to cell 4, they might force an inter-BSC handover, jumping between different regional controllers. Or even wilder, an inter-MSC handover, crossing the boundaries of entirely different switching centers, which are essentially the massive telephone exchanges of the network. The protocol has to bridge that call across these giant infrastructure nodes without even a single millisecond of dead air.
Section 4. Optimizing channel capacity. Handling network queues.
Imagine this absolute worst-case scenario. You've got a fast-moving user, a critical handover is queued up, but the target cell is totally congested. The connection is starving for a free channel, and it is about to drop. Enter the sub-rating algorithm. This is your ultimate network hack.
When that handover queue backs up, you need to manufacture capacity out of thin air. Magically, by executing this algorithm, you instantly split one full-rate traffic channel into two half-rate channels. Boom, you've immediately doubled your capacity in that cell. Sure, the voice quality might compress just a tiny bit, but it saves that queued connection from sudden death. If you're an engineer managing a jammed-up cell, like during a massive highway traffic jam, this mathematical trick is a total lifesaver.
Section 5. Mobility and location updates. Tracking user movement.
Obviously, to maintain a call while moving, we need to know exactly where the user is before they even hit dial. We can walk through the chronological mobility management flow to see this constant background chatter. Step 1, the mobile station switches on and performs an attach procedure. Step 2, as you move, the phone constantly listens and detects changes in its location area identity, or LAI. Step 3, the second it detects a new LAI, it proactively informs the network. And Step 4, the MSC and VLR verify your visitor status and update their routing tables. But what if this fails? Let's say you drive into a deep mountain tunnel. You hit a total loss of coverage before Step 3 can even complete. The network literally loses track of you. In that actual scenario, your location update fails, you become totally invisible to the network, and incoming calls go straight to voicemail until you exit that tunnel and reattach.
Section 6. Key Performance Indicators. Evaluating connection.
At the end of the day, your job security as a network engineer boils down to a very specific set of key performance indicators. To stay on the network's happy path, you have to avoid the most common protocol failures, which usually happen when the network misjudges that delicate balance between signal strength and bit error rates we talked about. If your algorithm is tuned right, you'll have absolutely zero excessive handovers. None of that bouncing back and forth between towers, which we call ping-ponging. You'll have no delayed handovers that drop calls, and no early handovers that waste resources. And most crucially, it all has to be fully transparent. Whether they're using voice or data, this entire engineering ballet happening in the background has to remain 100% invisible to the user.
Looking at the sheer complexity of these GSM protocols, the power thresholds, the sub-rating channel splits, the endless location updates, it is honestly a marvel that any of it works at all. But, with networks becoming so much denser, utilizing smaller cells, and leaning really heavily on cloud virtualization, it leaves us wondering, will the traditional edge-of-your-seat tower-to-tower handover eventually just be a thing of the past, replaced by something totally different? What do you think? Keep that in the back of your mind next time you check the connectivity bars on your phone. Thanks